In order to be able to read NMR spectra, we need to know exactly where different electronic environments will create different shadows. So we saw in the previous exercise how hydrogens that are in different electronic environments will absorb higher or lower energy. They'll need higher or lower energy in order to flip, because they'll have more or less electrons opposing the external magnetic field, so that the net magnetic field will be bigger or smaller in places. And since it's the net magnetic field that's holding the nuclei in a certain orientation, the weaker that the net magnetic field is, the easier it'll be to make the nucleus flip its magnetic orientation, and so the less energy it'll absorb. Now, on our little NMR graphs, that energy it was given on the x-axis, with the lowest energy on the right and the highest energy on the left. And these are given in relative units, units that are compared to the amount of energy it takes to flip the hydrogens in a molecule called TMS. That's tetramethylsilane. So the silane is referring to a silicon, and you just have 4 methyl groups coming off of that. So those hydrogens have a lot of electrons around them. Silicon is below carbon on the periodic table, so it's a little less electronegative. So the electrons are going toward each of those methyl groups, and so toward the hydrogens. So they have a lot of electrons around them. Those oppose the external magnetic field a lot, and it's easier to get those hydrogens to flip. So they absorb lower energy. And the absorptions for anything else are compared to the absorptions for the hydrogens in TMS. How far they are from TMS is given by relative units. They're called chemical shifts. They're described by the lowercase Greek letter delta, and the units for them are parts per million. And the reason why they're relative is so that scientists working in different laboratories with different strength magnets, so that the absolute frequencies that those would flip in would be different, can compare their results to each other, because the relative frequencies of molecules to that will be the same. So okay, we're going to have these chemical shifts. The chemical shifts are reflecting how much energy it takes for certain hydrogen nuclei to flip. The higher the shift, so the bigger the number, compare this, for example, with this, the bigger the number, the more energy you'll need to make the nucleus flip. Okay, so what I'd like to do is to rationalize these different numbers. Where are these numbers coming from? In the future, we'll have to know these numbers by heart. And in order to be able to read an NMR spectrum, we'll have to say, oh, I have a peak at 10, that's probably an aldehyde. So you'll want to know these numbers by heart, but in order to remember them, let's go through the reasoning behind them first. Okay, so first, let's focus on the 3 in the top left right now. These 3 right here. So the methyl, methylene, and methine. Notice that their absorptions are all around 1. They're close to 1. These are hydrogens that are on a carbon. And the reason carbon that's just bonded to other carbons. And the difference between these is how many other carbons they're bonded to. So if you notice in the very top one, the methyl one, the carbon that with the hydrogens on it is only bonded to one other carbon, and so it would be primary. Whereas in the second one, the methylene one, the carbon with the hydrogens on it is bonded to 2 other carbons, so it would be secondary. And in the third one, the carbon with the hydrogen on it is bonded to 3 other carbons, so it would be tertiary. All right, To understand why the hydrogens on those three types of carbons, we recognize that they're in a different electronic environment, so they'll show up in different places, but to understand why the shift is getting bigger, why it takes more energy to flip this tertiary nucleus, the hydrogen on a tertiary carbon, than on a primary or secondary. To understand that, we have to know first that carbon is slightly more electronegative than hydrogen. So the Pauling scale gives numbers to describe how electronegative an element is. The larger the number, the more electronegative. Carbon is around 2.55, and hydrogen is around 2.2. So notice what happens here. The bigger the number, the more electron density gets pulled away. Now, in this first one, in primary carbons, in the case of primary carbons, hydrogens on those are feeling a total of 2 plus 2.2 plus 2.2 plus 2.55 electronegativity around them. And so that's a total of 6.95. So imagine an electronegativity pole of 6.55 stealing electrons from this hydrogen of interest. Okay, let's compare that with a secondary carbon. Here, our hydrogen of interest feels a pole from 2.2, that's a hydrogen, 2.55 and 2.55, the two carbons. So overall, there's a net electronegative pole of 2.2 plus 2.55 plus 2.55, that's 7.3. So there's an electronegative force of 7.3 pulling electrons away from the hydrogen. And finally, in the tertiary case, our hydrogen of interest is right here. It's surrounded by 3 carbons, so that's 2.55 plus 2.55 plus 2.55. That's a net electronegative pole of 7.65. So those act even better to pull electrons away from the hydrogen. And so notice, remember in our fields, in our spectra, the x-axis is the chemical shift in parts per million, which is really telling us about the energy that these are absorbing. And you have the lower energy here, so that's TMS, which is 0, and the higher energy to the left. Overall, the electrons in the primary carbon over here, electrons are not being pulled away as much. They're only feeling a pull of 7.55. So you have more electrons around this hydrogen. Whereas in a tertiary carbon, there's a stronger pull stealing the electrons away, so you have fewer electrons around this hydrogen. They're being stolen by the other carbons. And so what that means is this hydrogen, this primary one, the primary one that has more electrons, that opposes the external magnetic field more, so that the net magnetic field is smaller, and it doesn't take as much energy to make those flip. They flip at around 0.9. But as you go to a secondary carbon, with a secondary carbon, there are fewer electrons there. They're getting pulled by an extra carbon around it, whereas this one only had one. And so there are fewer electrons, so the electrons oppose the external magnetic field less. So the net magnetic field is bigger, and they absorb more energy. It takes more energy to make them flip. They would absorb at around 1.2. And last but not least, in the case of a tertiary carbon, a hydrogen on a tertiary carbon, that's all the electrons there are being pulled by 3 carbons with slightly larger electronegativities. And so there are even fewer electrons around that, which means that those electrons aren't able to oppose the external magnetic field as much. So the net magnetic field is bigger. So it takes more energy to flip a nucleus in that bigger field. And so that gets shifted even more. So that's 1.7. So that's the reasoning behind the numbers here. The number to begin with is small because there's nothing really electronegative nearby. So these hydrogens are keeping most of their electrons. So the electrons are overall able to oppose the external magnetic field pretty well. And it's easier to flip the nuclei. But as you go from a primary to a secondary to a tertiary hydrogen, the carbon that the hydrogen is on, you have more electronegative atoms nearby. The carbons are ever so slightly more electronegative than the hydrogens, and so there's less electrons around those hydrogens. Those electrons oppose the external magnetic field less, so they feel a stronger field and it's harder to get them to flip. You need more energy to get them to flip. So that's the rationale behind those first three. So we've considered those. There's a similar trend with what happens to when you have very electronegative atoms nearby. So we were just talking about carbons and hydrogens. Carbon is more electronegative than hydrogen, but not by a lot. In the case of halogens, the difference in electronegativity is much bigger. So if you take that same molecule with the hydrogen of interest, but instead of carbons around it, we put a halogen. Symbol for a halogen is usually just a capital X. And that could be fluorine, chlorine, bromine, or iodine, anything in group 7A. Those are really electronegative, so they're really going to pull electrons to themselves. And so now this hydrogen has even fewer, it has very few electrons around it, or I should say electron density around it. Because there are fewer electron density around it, the opposition, they're not as able to oppose the external magnetic field as much. So the net magnetic field is bigger, and it's harder to flip a magnet in that field. So you need even more energy to flip that nucleus. You need even more energy, and so the greater amount of energy is expressed by a larger chemical shift. Those chemical shifts are just relative units to say how much energy you need to flip the nucleus. The bigger the shift, the more energy you need. So when you have these electronegative halogens on a molecule near a hydrogen, they make it harder to flip that hydrogen. With an alcohol, the situation is very similar. So we've considered this now. For an alcohol, the shift is very similar. We have that same, instead of having the hydrogen on a carbon, we have it on an oxygen. Oxygen is so electronegative, it pulls the electrons to itself. It becomes slightly negative and the hydrogen becomes slightly positive. The hydrogen has so few electrons around it, or I should say electron density. Because there are so few electrons around it, they can barely oppose the external magnetic field. And so the net field is very strong. So it's very hard to get a magnet to flip in such a strong field. You need even more energy, and the chemical shift gets bigger. The chemical shift which represents the amount of energy that you need to shine on that nucleus in order to get it to flip. And you're shining the energy on the nucleus as radio waves. So there would be an even higher frequency of radio waves that absorbs that. Okay, so far the differences in chemical shift that we've seen have to do with electronegativity. Electronegativity steals electron density from the hydrogens, and as we've seen so often before in the last two videos, when you have electron density stolen from the hydrogens, as you have fewer electrons, you need more energy to flip the nucleus. So that's the reason for the chemical shifts we've seen around these more electronegative atoms. That's 5 of the patterns. The other patterns have, the numbers for them are explained by something called magnetic anisotropy. So let's talk about that. So the word anisotropy, the A here means not. It's the same prefix as in atom, which means not cuttable. You just have an N there so that the A doesn't mix in with the I sound, doesn't sound bad with the I sound. So it's not. Iso means the same or equal, and tropy is just a place. So magnetic anisotropy is where you have a magnetic field that isn't the same everywhere in space. It's not the same at all places. I think a good example for this to start with is a benzene ring. Usually a benzene ring is drawn with alternating single and double bonds. When you have those double bonds, you have them because there are parallel p orbitals on those atoms that overlap to create the bond. Every time you have a pi bond, you have parallel p orbitals. But notice there are parallel p orbitals between every atom here. So the electrons aren't just stuck between two, they spread out and fly around the whole molecule. So when you apply an external magnetic field, the electrons that are flying around orient their magnetic field. They move around so that the magnetic field they produce opposes the external magnetic field. But the magnetic field that's produced isn't the same in every place. It doesn't point down everywhere. When the magnetism points in one direction, so let's say north is pointing down, that creates the opposite type of magnetism on the opposite side, south. It's as if you're creating a mound on one side and a hole on the other. And when the mound gets big enough, it falls back into the hole. And so the magnetic field that you're making inside of the swirl of electrons that opposes the external magnetic field falls back in on itself. And so you get this curl of magnetic field. Now notice, the magnetic field points down in one place and up in other places. It's not the same in every place. So that's anisotropy. Think about how that would affect a hydrogen on one of these carbons. That hydrogen, the electrons don't make the magnetic field around that hydrogen smaller. They don't act against the external magnetic field. They go with it. By that point, the magnetic field is curled around. It's getting sucked into that opposite end of itself. And they add to the external magnetic field. So the overall magnetic field, which is the sum of the external magnetic field and the one that's produced by the swirling electrons, is even bigger. And because it's bigger, it's even harder to get the nucleus to flip. This is being held really tightly in place by the net magnetic field. So it's really hard to get it to flip, because every time it tries to move, it gets pushed back into place. Very hard to get it to flip. And so in order to get it to flip, you have to add a lot of energy. In other words, the delta is going to be big. So for the hydrogens that are on a benzene ring, if you look back here, those show up at very high deltas. You need a lot of energy to make those flip, because the magnetic field produced by the swirling electrons opposes the external magnetic field inside, but then adds to it outside because of that magnetic anisotropy. So So that explains that high number for this aryl group. Now if the hydrogen gets a little further away, so let's say instead of just the hydrogen, you have a carbon, and then the hydrogen is coming off of that, so it's not directly attached to the ring, it's on a carbon that's attached to the ring. In that case, it still feels the added magnetic field, but because it's further away from the source of the magnetism, it's weaker. The added field is weaker. So, for example, if the magnetic field that's coming from these swirling electrons is really big on the hydrogen that's close to the source of the magnetism, close to the ring, it will be smaller for the hydrogen that's further away from it. As you get further from the ring, the magnetic field that you're making gets weaker. So you'll still be adding a magnetic field to the external magnetic field, but the net magnetic field won't be as big as it was for the hydrogen that was closer to the source of the magnetism. And so if you look back at this table, you'll see that for this aromatic methyl group, the hydrogens that are one carbon away, they don't take as much energy to flip them because the magnetic field from the anisotropy that's adding to the external magnetic field isn't as big. So they're smaller than the aryl hydrogen, but they're larger than just a normal primary hydrogen, because the anisotropy is still adding a magnetic field to the external magnetic field. Okay, so we've explained these now. So we have 4 left to explain. The rest of these all have to do with anisotropy. It turns out that when you have a pi bond, so pi bond is where you have 2 parallel p orbitals and they overlap, although the overlap is interrupted in the middle. They do overlap, so that ultimately you sort of get a big orbital like this, where the nuclei would be inside. That's a pi bond. You have that any time where you have a double bond. And the electrons in a pi bond can swirl around the pi bond in the same sort of way that they swirl around the benzene ring. So that if you have an external magnetic field, those electrons will swirl around in a way so that the magnetic field they produce opposes the external magnetic field. But if that's the north side, when you create that, it creates a south side on the opposite end. And so, just like if you have a big mound and you have another ditch, it gets sucked back into it. And so the magnetism loops back around and falls back in. And so anytime you have a pi bond, you have that same magnetic anisotropy. Magnetism's pointing down in the middle of the bond to oppose the external magnetic field, but pointing up outside of the bond to add to the external magnetic field. So, if you have something like a double bond, this hydrogen here, let me copy this, but instead of the orbitals, I'll show you what it looks like with the double bond. You have the double bond here. In the case of this, the electrons are swirling around here in order to produce a magnetic field that goes down, but it loops up and goes back around. And so if you're a hydrogen coming off of a double bond, you're feeling this magnetic field a lot. That is in the same direction as the external magnetic field. So they add together, and the net field is bigger. So when you try to flip the nucleus of that hydrogen, you need more energy to flip it. And so if you look at the hydrogens on, say, a double bond, notice those numbers are relatively large. Compare a primary hydrogen that's not near a double bond. It's at 0.9. Look at how much bigger, how much more energy you need. That's because of the magnetic anisotropy, the magnetic field coming from the electrons adding to the external magnetic field. So that's the reason for this vinylic hydrogen. And vinylic, that means that the hydrogen is attached to an atom in a double bond. Kind of like with benzene, we saw that if the hydrogen is not attached to the atom in the double bond, but is one atom away, one atom away, it still feels the magnetism, but because it's further away, it doesn't feel it as much, so the area there would be smaller. The net magnetic field would be smaller, and so it would be relatively easier to flip the nucleus of that hydrogen. You would need less energy to do it. So if a hydrogen is not attached to the double bond, like it is in vinylic, but it's one atom away from that, you don't need as much energy to make it flip. And we kind of saw that similar thing happening with a hydrogen attached to the benzene ring, needing a lot of energy to flip, and if it's instead attached to a carbon that's attached to the benzene ring, you don't need quite as much. So, if you're one atom away from an atom in a double bond, you're called allylic, and so these allylic hydrogens won't need quite as much energy to flip as a vinylic hydrogen, but they need more energy than just a normal primary hydrogen on a primary carbon because of the magnetic anisotropy. For a similar reason as the vinylic hydrogen, the anisotropy that adds magnetic intensity to the external magnetic field makes it harder for that nucleus to flip. That also happens in the case of an aldehyde. You have the same pi bond, and so you have the same pi bond. It's just to an oxygen. Right, an aldehyde is where you have oxygen double bonded to a carbon and a hydrogen on one side. So imagine if you take that and you flip it to the side, you have the scenario we were just talking about. So you get the electrons swirling just like before. They swirl in such a way as to produce a magnetic field that opposes the external magnetic field, but when you create that, it gets sucked back into itself, and that creates this magnetic anisotropy. And where this hydrogen of the aldehyde is, the magnetic field is in the same direction as the external magnetic field, so they add together. To create a larger magnetic field, which is harder to flip the nucleus in, because it's being held more tightly by a stronger magnetic field. So you have that effect. But if you compare, you have that effect anytime you have this pi bond, so it was a big number there and it was a big number here. But you'll notice the number for an aldehyde is even bigger still, because the magnetic anisotropy effect is adding to the electronegativity effect that we discussed before. Not only do you have this magnetic anisotropy, but in an aldehyde, you have an oxygen that's really electronegative. It pulls the electrons closer to itself, becomes slightly negative. The hydrogen ends up being slightly positive, and now there are really few electrons around the hydrogen that can swirl around in their orbitals to oppose the external magnetic field. And so this is barely shielded against the external magnetic field at all. It can't sort of defend itself as much against this external magnetic field. And so you have the effects of magnetic anisotropy and electronegativity influencing an aldehyde and taking electrons away from the aldehyde and then adding to the external magnetic field And that's why it takes so much energy to flip that nucleus. Okay, so we've explained everything here. Oh, up to aldehydes. Carboxylic acids, you notice they're even further down because the hydrogens both have the effect, they're feeling the effect of the magnetic anisotropy on that pi bond there. And they're feeling electronegativity from 2 oxygens, so that pushes them even further down than an aldehyde. So they're really, really far. All right, last but not least is the hydrogen on an alkyne. So the hydrogen on an alkyne. For that, we have to picture how the electrons are flowing around in the alkyne bond. Now alkynes will have 2 parallel p orbitals. One will be, say, the py's. And let me separate these, even though they would naturally overlap, just so we can visualize them a little better. And the other would be the px's. So you'd get overlap between the py's, and you'd get overlap between the px's. And those are your 2 pi bonds. And what these end up doing are creating a sort of, let me do this in a different color, they end up creating a sort of cylinder. A cylinder of electricity, of electric charge. So you've got this big cylinder here that the electrons can end up flying around in. And on this cylinder, you'd have the hydrogen over here. Oops. If you think about the alkyne, these would be the carbons. You'd have the 2 pi bonds, a sigma bond, an R group over here, and the hydrogen over here that would normally absorb the radio waves. So the hydrogen would be like right here. And the way that the electrons fly around in this sphere is not horizontally, like we were showing before, but rather they're around, they move around vertically here in this cone. So if you have an external magnetic field that's pointing this way, the electrons will move around in such a way as to produce an opposing magnetic field. And notice that the hydrogen on the aldehyde is in line with that. So this eventually coils back around and you get the anisotropy just like with alkenes. But the hydrogen is in line with the part of this that's opposing the external magnetic field. And that's why this hydrogen here is not nearly as, you don't need nearly as much energy to flip it as you would need for a double bond. Because the magnetic field that's produced by the swirling electrons opposes the external magnetic field in the case of the alkyne. Whereas in the case of the alkene, it added to it, just because of the orientation of the magnetic field. So it's smaller. You need less energy to flip an alkyne hydrogen. Notice, though, that it's bigger than a normal primary. It's bigger than a normal primary carbon. Okay, so these are the different shifts. Now what you will want to do is to know these by heart. You'll want to see peaks at these different areas, these different shifts on the x-axis. So you'll have that x-axis, that's a delta. When you see something at 10, when you see a peak at 10, you want to say, oh, probably an aldehyde. When you see a peak at 1.2, you'd say, oh, probably a CH2. And those are going to be puzzle pieces that will then fit together to see the structure of a molecule. But the first step is to memorize these different shifts. So in the next, this is just a background video. This video is to explain the trends that you see in these shifts. And what we're going to do in the next video is to apply these shifts to specific hydrogens and specific molecules and predict about where the peaks will be in those molecules. There's one last comparison I'd like to make just as an addendum. We talked at the very end about why the energy you need to flip this nucleus on a hydrogen on an alkyne is smaller than the energy you need to flip a nucleus of a hydrogen on an alkene. It's because the magnetic fields opposing the external magnetic field are oriented differently. In the case of an alkene, it adds to the external magnetic field. In the case of an alkyne, it opposes it. But there is one other question you might have had, and that's how come this is bigger than the corresponding hydrogen with all single bonds? Why does it take more energy to flip this hydrogen than this one, since the carbons on both of them are bonded to 3 other carbons? And that has to do with the orbitals. So this carbon here is sp3 hybridized. It's not involved in any pi bonds. This carbon here is sp hybridized. It has 2 pi bonds. You need a p orbital for each of those, so there's only 1 p orbital that has left to mix with the s orbital. So it's sp hybridized. And when you think about what those mean, these are really recipes for how to make these mixed orbitals. When you make an sp3 orbital, you mix an s orbital with 3 of the p orbitals. And so this is going to be 75% p, which means it's going to be pretty stretched out like a p orbital is. Whereas with an sp orbital, you're mixing 1 s with 1 p. So this is, instead of being 75% p, this is only 50% p. So this is going to look much more like an s orbital. So the s orbital really adds to one of the lobes to really affect it. And what you'd want to notice here is that the sp3 orbital keeps the electrons further away from the nucleus. The nucleus is at the node, so it's right here. It's right here. In the sp3 orbital, the electrons are far away from that, whereas in the sp orbital, they're really close. And so, because they're closer in an sp orbital, they're more neutralized. This charge here is not quite as intense as the charge on an sp3 orbital. And so it's like having fewer electrons around the nucleus. Fewer electrons around the nucleus means it can't oppose the external magnetic field as much, so the net magnetic field is stronger, and you need more energy to flip the nucleus. So that's the reason for the relative numbers between those two.